Okay, so today we're going to be talking about homework 3, which goes over a many to one recurrent neural network problem that is trying to achieve classification prediction for sentiments that were expressed on February 2015 and on Twitter for about U.S. airlines. So that's the data set. We're going to go over the code here. We've got our imports, we've got the code that was provided by the professor, and I've added a shuffle so that at each batch the data is shuffled. I didn't think about this until I got to the LSMT, I have struggled with that. And I didn't use it for all of the data, but the purpose of it is to make sure that it's not the exact same code running through every time for every epoch in the exact same order. So it just presents it in a different order. Hopefully that mixes it up a bit. Okay, then we bring in the data, we encode the sentiments, and we tokenize the text, and we add some padding so that all of the are you okay? So that all of the sequence lengths are the same length going through. So I wanted to point out in here that the data was imbalanced, and I did some digging with that and did some various coding to analyze that, and we've got a chart here for 71.43% of the data has a high confidence score in the sentiment label that was provided, and then 7.84 is medium high, 19.11% is medium low, and 1.61 is very low. These confidence scores really ranged from 0.34 to 0.39, I think. So that just to me seemed like it shouldn't be part of the label teaching process, but I don't know. So down here we have a breakdown, and the imbalance is further exaggerated when we look at just the high confidence sentiment labels, and negative tweets represent 70.7% of that. So in the total data, the negative tweets are 0.63%, 63% of the data, and so when we just look at the high confidence, it goes up to 70.7%. So I didn't do really anything I tried one thing to balance the classes more, but it didn't work, and I decided not to fool with it too much because it wasn't part of the scope of this problem. But I would imagine that it is something that affected the validation and training scores that I got. Okay, so we've got our train test split. So we're splitting it into training and validation sets, 20% validation, 80% training. And then we are going to take those sets and turn them into a generator with our generator. our one hot generator so that it one hot encodes them in batches. And it does that dynamically throughout the trial. Okay, so we're building our RNN model, and I tried to make it compatible for making all the changes that we needed to make, including passing in the build that would be used. So this would be the LSTM and the simple RNN. And then we've got all of our parameters that we're going to be passing in. We've got our parameter grid that's created randomly. And then we've got our training session here, or our training method. And so we selected top performers based on average across average validation accuracy across all epochs, and we replaced those along the way with higher and higher scores and lower scores for the bottom performers. Then here's our trials running. We've got save. Here's our plot functions, our plots. This is the latest and greatest LSTM that was run with the shuffled generators, and with limiting the parameters to the ones that were most ideal from our experiment 1 with simple RNN. So cutting out some of the ones that didn't work as well, and then also I added in these higher unit nodes to capture what that was like for the LSTM RNN model. The scores weren't profoundly different, but they were a little different when I did that. Okay, and plot loss, further analysis, the heat map, I just put it into a CSV file, a data frame to CSV file, so that I could do some funky graph stuff with it and look at the data in a different way. Over here we've got our report. Here I'm talking about the imbalance in the code, and we've got all of our formulas that we are using for the RNN, and also keeping the formulas that are the same from previous models, but adding in the new ones. Our performance metrics, of course, are accuracy and loss. And for the overfitting, I gave examples here. This is the simple RNN, which has big gaps indicating overfitting, and the small gaps, and you can't see it here, but this is like 0.03, 0.06, and 0.05 or something like that, and is the distance between these gaps in values. So this is not really a great example of overfitting, but it is a good example of how overfitting is mitigated by the LSTM. So even though I didn't get a profound difference in the total average accuracy scores or highest accuracy scores or ending accuracy scores than the simple RNN, but what I did see was effective overfitting mitigation. So, and I imagine, going back to what I was saying earlier with the imbalanced data and not handling that properly, that may be affecting some of those accuracy scores with the, and the uncertainties in the data. So we've got, what I would call 7, 16, 17, 18. 18% of the data is what I would call confusing for the model. So, I don't know. I thought that we at one point we talked about giving clear representations and not giving giving confusing or ambiguous representations during the training portion, so that the model could get a clear perspective before it moves on to bigger and greater things. So, yeah, okay, harping on that. I'm out of time. I'll go on a little farther. We've got an anomalous situation here, where the data flatlines at 0.645, and it flatlines down here at something like 0.623 for the training accuracy. This 0.645 was something that I actually saw in early trials of both of the models. For the simple RNN, I quickly identified the culprit and got rid of that hyperparameter setting to focus on things that weren't identical. They were all identical. The the training accuracy varied a bit, but the validation accuracy was always 0.645, and the culprit in the simple RNN was a learning rate of 0.001, and the main culprit, it seemed to be in the LSTM, was using just 16 hidden units. So it makes sense to me that those would probably have problems, but the part that doesn't necessarily make sense to me is that it was always exactly 0.645. But I think once again it goes back to the imbalance in the data. And so once the hyperparameters were set to unfavorable settings, the model could, the majority of the time, predict the main class, and still achieve. So if the model was just willy-nilly, randomly assigning and had no idea what it was doing, and just randomly picking which class and what assignment, then it would be 0.3 or 33.33% for each class, or it would achieve only 33.33% accuracy, because it would be a third. It would be getting a third of them correct at a random pace. So the fact that it can achieve 0.645, I think, is attributed to the imbalance in the data, and it reaches some sort of learning stagnation because of the hyperparameters, but it still performs at that level because of how, whatever the distribution is, that it's able to pick up on in this imbalanced distribution. So somewhere in these numbers, you could probably discover why it's 0.645. Okay, I'm way over on time. I'm exhausted. I'm rambling. I'm not talking very well. So I guess we'll leave it at that and let you look over the report for the rest of it. Thank you.